the opportunity to talk here. It's especially nice to see that Andy's taking Maximising the RISC very seriously, but maybe a little too far in this instance. So this is about as far from a synthetic talk as you can get. Now moving from proper chemistry to theoretical chemistry or theoretical physics, and looking at the role of vibronic coupling to understand the reverse intersystem crossing mechanism in these TADF molecules. So a quick outline, following on from the previous talks, a description of delayed fluorescence. And then does the reverse intersystem crossing rate actually matter? If you want to improve devices, is this an important factor that we have to consider? Can we use organic emitters? Well, the answer is obviously yes, but I'm going to expand on that a bit more. And the role of vibronic or non-adiabatic coupling in this process. And then inspired by an undergraduate student who wrote in a recent lab report that the limitation of computational chemistry is it's not real. I'm going to compare to some experimental results and then try and turn our simulations into a more general model description of what's going on. And then some conclusions. So I don't think I need to spend too long on this, as it's another Jablonski diagram, another description of the delayed fluorescence. But as we've seen before, we have a singlet. The general picture is a singlet state and a triplet state that are close enough in energy that thermal activation can drive reverse intersystem crossing back into the singlet state, and it can emit as delayed fluorescence from the S1 state. And again, very similar to before, in the fact that we have the splitting from the electrical excitation of the singlets and the triplet states. And the main focus is if we want to have efficient devices, we want to get as much of this triplet population out as possible. And as this has been so well explained, I won't spend any longer. So delayed fluorescence has been around an awful long time. So the citation here is from 1961, but I did actually find a paper in a French journal yesterday in which they talked about fluorescence of long duration, which was published in 1929. So this is certainly not by any means a new process at all. And essentially from this paper onwards, the picture of delayed fluorescence has been a firmly equilibrium process. You consider that the fluorescence rate of your system is slow. And so the singlet state and the triplet state form an equilibrium. You can write an equilibrium constant. And this equilibrium constant is actually then defined by the Boltzmann statistics and the relative degeneracies of the two states. And in this case, you can write the rate of thermally activated delayed fluorescence, i.e. the reverse intersystem crossing and the fluorescence, as this Boltzmann statistics multiplied by the fluorescence rate. So this thermal equilibrium process, you can see immediately that there's no role of reverse intersystem crossing rate at all. So what it's saying is that the delayed fluorescence is completely independent of this step. And this motivates essentially designing your molecules based on purely the energy gap between the two states involved, and as was excellently described in the first talk, trying to make your molecule more rigid to stop the non-radiative decay and increase the fluorescence rate. But if we're going to apply this for OLEDs, then we want to obviously increase the fluorescence rate as much as possible and try and get out as much light. Well, for most of the TADF emitters reported in the literature, this equilibrium picture breaks down. So we have to move to a kinetic picture, which is taken from Fernando's paper, which was published last year. And if we solve these kinetic rate equations, then essentially we can see here that the rate of the T1, obviously, as one would expect clearly depends on this rate of reverse intersystem crossing. And as is well known in this room, because the amount of population in the triplet state is important for especially things like quenching effects, it's going to be crucial to try and maximize this reverse intersystem crossing to make sure that we avoid these kind of quenching effects and have the most efficient devices that we can. So a lot of the work on delayed fluorescence, starting with Macmillan's group in the States in the 70s and 80s, was on copper 1 emitters. And the reason that this was the focus is that the spin-orbit coupling in these systems is a lot weaker than it is for iridium. And so they're not particularly phosphorescent. They have a long phosphorescent lifetime. And so you have this opportunity for the reverse intersystem crossing. And here the reverse intersystem crossing is very well described in an equilibrium picture, because you only have, in most of the important emitters, you have a T1 and an S1 charge transfer state that are very separated from all the other excited states. But these are quite weakly spin-orbit coupled. And the reason for this is that actually the spin-orbit coupling, you have the atomic spin-orbit coupling constant and then the angular spin momentum. And so this is responsible for the heavy atom effect. But it's important to remember that also this integral. And to have a large spin-orbit coupling, any change of the spin must also be compensated by a change in angular momentum. And what this means is that if you have two charge transfer states, the spin-orbit coupling is going to be, by definition, very small, if not zero, because your change of spin is not changed by change of angular momentum with the orbitals involved in your excited state. And so for a range of systems that we've looked at, we found that actually the reverse intersystem crossing rate is pretty much hardwired by the spin-orbit coupling. And okay, a little variation of gap. This is done with a classical Fermi golden rule, and you get about 10 to the 5 seconds to the -1. But pretty much whatever you do, it's hard to modify this in a very big way. So we're talking about crossing between two spin states. Your first reaction when we think of organic species is, this is not going to happen, there's no spin-orbit coupling. Well, what we have to remember in this case is that the efficiency of the crossing between these two states is not only dependent on the spin-orbit coupling, it's depending how well these states mix. And if we look at first-order perturbation theory, then they'll mix with the close-lying S1 like this, with the prefactor A. The prefactor is the value of the spin-orbit coupling divided by the energy gap. Well, as this energy gap being small is already a requirement for delayed fluorescence, we can actually have the possibility, as shown in the previous talks, to get efficient reverse intersystem crossing without necessarily particularly large spin-orbit coupling. However, this still doesn't solve the problem that if you have two charge transfer states, the spin-orbit coupling between them is formally zero. And okay, this doesn't work if the spin-orbit coupling constant is zero. And as has also been said in the previous two talks, there's been increasing amount of discussion about the local excited triplet states being involved with this. But even so, the spin-orbit coupling between the locally excited state and the charge transfer singlet is still very weak. An example of this was recently published in Journal Physics MC by Chen et al., in which they took a number of molecules, some donor-acceptor and donor-acceptor-donor molecules, calculated the spin-orbit coupling, and then using Fermi golden rule, they calculated the rate of reverse intersystem crossing. And they found values of about 10 to the 2 seconds to the -1 for all of the systems that they calculated, compared to the experimentally reported values of 10 to the 6 or 10 to the 8, 10 to the 9. And this compares to the rates you can find in the literature that vary by 6 orders of magnitude. So these agree very nicely with the lower range, but clearly you've got some very efficient, some very relatively quick reverse intersystem crossings rate, which theory in this case is missing by about 6 orders of magnitude. So, as a way of describing this, there was a very recent paper by Crystal Mariam, and looking at this molecule, and what she proposed is that actually motion along vibrational coordinates was responsible for more efficient reverse intersystem crossing. And in this case, the charge transfer states are very separated from the local excited states at equilibrium. But as you move along this carbonyl stretch, these potential energy curves actually come close and they begin to mix. And so you get a vibronic contribution to the reverse system crossing. So you have the spin orbit coupling value at the equilibrium, and then it's modified by an increasing spin orbit coupling as you go along this potential energy surface. Now, the problem in this case is that the quantum chemistry that you use is an inherently static picture. You've calculated dots at your point, you've connected them with lines, but vibrations, a lot of it is clearly a dynamical process in a multi-dimensional potential energy surface, and so we have to go beyond, to get a full mechanistic understanding, we have to go beyond this static picture and understand this process in a dynamical way. So my interpretation of where we are at present is that most of the molecular design to date has been based on this equilibrium description, essentially trying to minimize the gap between the two states. But of course, the spin orbit coupling between these two charge transfer states is weak at very best. Some very high reverse system crossing rates which remain unexplained, and certainly cannot be explained with a simple Fermi golden rule description. And there's clearly something dynamic going on that we have to explain. So this molecule will look familiar to a lot of you. For us, synthesizing this donor-acceptor molecule is very easy. A few clicks on the computer. It's a lot easier than the donor-acceptor donor molecule because it's smaller and we don't have to worry about so many excited states and so many degrees of freedom. So, as has already been discussed, this is donor-acceptor charge transfer complex, and the low-lying excited states that play a role in this, if you were identified to be 3 in particular, so this locally excited triplet state on the donor unit, and then the triplet and the singlet charge transfer. Okay, so we can say that these are the 3 excited states that we're going to have in our model. The other excited states are quite separated in energy and they don't play a massive role. But then if we're going to look at the dynamics, we have to determine which vibrational degrees of freedom are important. So, being that we use time-dependent density functional theory, it's very efficient. We can, and we can also use molecular symmetry in this case. We can calculate essentially potential energy curves along a range of normal modes which are potentially important, and then we can fit these to a model Hamiltonian expression that we have. And from this fit, what we get out is the couplings between the 2 triplet states. So there's this coupling that arises from vibrational motion. And from a number of normal modes that we calculated, there are 3 that we found to exhibit relatively strong vibronic coupling between the lowest locally excited triplet state and the charge transfer triplet state. And these just happen to be torsions, or dominated by torsions around this donor-acceptor dihedral. Okay, so once we fit these, we set up a relatively simple model Hamiltonian, which is composed of 3 states depicted here. You have a singlet charge transfer, a triplet charge transfer, and a locally excited triplet, and 3 nuclear degrees of freedom, which are all essentially this donor-acceptor angle. The locally excited triplet and the charge transfer singlet are calculated by are coupled by spin orbit coupling. This was calculated also with time-dependent density functional theory and is about 2 centimeters to -1. The 2 charge transfer states, the spin orbit coupling is 0, but they're coupled very weakly by this hyperfine interaction. This value here was actually taken from typical EPR measurements. It's a typical coupling. So it's not actually calculated, but as I show you later on, it really doesn't have a massive role. And then from the fitting on the previous slide, we find that the singlet, the triplet locally excited and the triplet charge transfer are coupled by bipronic coupling, and this is an order of magnitude stronger than any other coupling. So this is the strongest coupling in the system. This is just it written. So very briefly, one slide. So we take this model Hamiltonian and we do quantum wave packet dynamics. The reason for doing this is that we have a model Hamiltonian, but we know that the nuclear motion, the wave packet motion on this excited state is exact. So we're explicitly solving the time-dependent Schrödinger equation. We do this in 2 forms. So, well, to do this, we use the so-called multi-configuration or time-dependent hierarchy method. The reason for doing this is it allows us to treat larger systems. So, quantum dynamics scale exponentially with the number of degrees of freedom. What's different about the MCTDH approach is not only does it have time-dependent coefficients to describe your wave packet, the basis functions that you use are also time-dependent. And essentially what this means is that if you imagine that times 0, these are your basis functions, not only do the coefficients of each basis function change, but the position and the shape of these basis functions also change. The advantage of this is that you need less to convert your calculation and you can treat more nuclear degrees of freedom. And we do this both in a standard quantum dynamics package way where you have 0 Kelvin, and also a density formulation in which we can start at 300 Kelvin. Obviously, temperature is quite important in reverse systems. So, to begin with, we looked at the intersystem crossing. So, we initially excite our wave packet into the singlet charge transfer state, and what this graph is showing here is that the amount of this wave packet that's crossed into the triplet local excited state after 1 nanosecond. The black line is the population in the triplet local excited state using the Hamiltonian that I've described thus far. The green line is that it's exactly the same dynamics where we've taken out the hyperfine interaction. And as you can see, it basically has almost no effect. This dark blue line, on the other hand, is when we've taken out this vibronic coupling here. So if you take out the vibronic coupling between these two states, you kill this transfer. The red line is actually if you increase the vibronic coupling by 10%, and the blue line is if you decrease the energy gap between the charge transfer states and the local states. This is expected it would increase. The closer energy, so it increases. So now if we perform the same dynamics, but going the other way, these are now at 300 Kelvin. Again, the black line, the model Hamiltonian that I've described, but in this case we're starting from the triplet local excitation, and this is showing the population of the singlet charge transfer state of the function. Again, the green line, we've taken off the hyperfine interaction, no change. The blue line, we've taken off this vibronic coupling. So again, by removing this vibronic coupling, we're completely killing the reverse intersystem crossing. So what is the mechanism for this? Well, clearly, if we're looking at transfer between these two states, and coupling between these two states is playing a big role, we no longer can just look at Fermi golden rule, first order perturbation theory, where we're starting from some initial state, we're going to some final state via some interaction. So we have to move to second order perturbation theory, where we're clearly going from some initial state to some intermediate state, and then a final state. The obvious kind of route for this is then starting the triplet local exciton, go to the charge transfer triplet, and then hop over onto the singlet charge transfer. And I've already showed you that if you turn off the hyperfine interaction, it has no effect. So clearly this is not the pathway that it's undergoing. So what's actually happening is, because of this very strong coupling, you get efficient reverse internal conversion to the triplet charge transfer state. And this forms very quickly, and actually you have an equilibrium between these two states, which is dependent on the magnitude of this coupling. And then you get a second order term, which then goes from the triplet charge transfer through the triplet locally excited state into the singlet charge transfer. And the reason why that this is efficient is that this route takes advantage of the strongest couplings, but also the good Frank-Gondon overlaps between these two states because they're almost degenerate. So here this just reiterates this mechanism, and this is the population of these triplet charge transfer states. And you can see again the black line, the original Hamiltonian, you essentially very quickly in all simulations reach an equilibrium between these two states. So the population of this state remains virtually constant after a few hundred beacons, like a few hundred beacons, a few tens of beacons. So the first order coupling is weak. which really shows that the vibronic coupling is crucial if you want to get this faster reverse inter-system crossing. And there's no direct second order pathway. It has to first form this equilibrium and then go via this maybe slightly unintuitive route. Okay, so as I knew Jonathan was talking first, I was rather lazy and I just took the graphical abstract from his KenCom paper. This works, this correlates incredibly nicely with his results, because as he was reporting, when you put a bulky group to restrict this donor acceptor angle, you kill the TADF and get phosphorescence. This is exactly what we're seeing. The vibronic coupling responsible for promoting this efficient reverse inter-system crossing is this dihedral angle between the donor acceptor unit. So if you stop that, you're going to stop the TADF mechanism and therefore promote room temperature phosphorescence. The other recent experiment that actually the interpretation provided is different, but it actually correlates exactly with this. There's a time-resolved DPR study in which they looked at a range of TADF molecules. And essentially, what you're seeing in the time-resolved DPR is the local exciton, the local exciton triplet and the charge transfer triplet. And what they found by fitting the experimental signal is that the more efficient, the more population of the charge transfer triplet they found, the more efficient this reverse inter-system crossing was. And what they concluded was, actually, if this is more populated, it can go via this way, so you get to the hyperfine interaction is important. But as I showed you previously, this increased population of the charge transfer triplet is entirely consistent with this vibronic coupling picture, because the stronger the vibronic coupling, the larger the population of this charge transfer triplet, and therefore, and also the faster this second order and this reverse inter-system crossing is. So again, although the conclusions they drew are not entirely the same, the picture that we present is exactly consistent with these experimental results. So we can then take this into a more modeled description, because essentially it's obviously well known that the charge transfer states are going to be much more sensitive to the environment than the locally excited triplet state. So this is the case we have in the molecule that we study, in which the locally excited state is lower than the charge transfer state. But if you change the environment, you make them degenerate, or you shift the locally excited state above, exactly the same mechanism will happen, provided that you have this, the gap is small enough for this thermal equilibrium and population between them. And again, if we look at the reverse inter-system crossing rate as a function of these gaps, we can see that actually the gaps between the charge transfer states, this black line, is slightly more important. Okay? But the main thing to take from this is that there's two gaps you have to consider. You have to consider not only the gap between these two, but also the gaps between the two charge transfer, which are going to determine the Frank condor. And this is going to determine the mixing. Okay, so with that, just leave me to say, I hope I've demonstrated that non-Born-Oppenheimer effects are going to be crucial for the reverse inter-system crossing rate. Any mechanism involving just two states is going to be inherently slow. Vibronic coupling gives you this strong second order pathway, which also I hope I've convinced you can explain some recent experimental observations, and also reveals this dynamical mechanism for reverse inter-system crossing. It's important that we don't just say, look at the S1T1 gap. We've got two energy gaps in essence to converge. And I think maybe most importantly is this emphasizes the need not to go beyond the Born-Oppenheimer approximation when we're considering the design, and not just the static picture provided by quantum chemistry. It's very important to consider these couplings if we're going to optimize these devices. So this just leads me to thank people involved. Jamie did all the work on the organic systems, and Stuart did a lot of the calculations on the copper system. Andy and his group was many useful discussions about the mechanism. Thank you for your attention. These people for funding. And then a shameless advert if you know anyone that might be interested in theory. Thank you for your attention.